Before we look at an example of OR, where the events are not disjoint using probability rule number 5, we need to illustrate how to find the probability of A and B using logic. Later we will learn two rules for finding the probability of A and B, but these will mostly be used for finding probabilities in repeated sampling. Notice in our next examples that we do not need any rule to find the probability of A and B. Be sure to avoid using a rule to find the probability of A and B in similar problems. One final comment about these questions. Although there are instances in practice where finding the probability of A and B, or the probability of A or B, might be of interest, for the most part, the probabilities we will be finding in the next few examples have no clear practical use other than to illustrate these probability rules. These probability rules are important, but more in the underlying theoretical probability that arises in statistics than for the actual need to answer the kinds of questions we present. When we get to the next section on conditional probability, that will change entirely, and we will again have an excellent reason for understanding the interpretation of the results of our calculation, in addition to gaining appreciation for the rules being presented. To begin, let's find the probability that the randomly selected individual is in the oldest age group, 65 plus, and requires special equipment. In order to be counted, an individual must satisfy both of these events. There are 611 individuals who are in the 65 plus age group and answered yes to the question about the need for special equipment. We write the probability of 65 plus and yes equals 611 divided by 6582, which is about 0.0928. Note that we are still dividing by the total in this case. As we learned in the exploratory data analysis unit for KCC, the result is much different when we restrict our calculation to a certain row or column. We will address those types of probabilities in the next section. Let's look at one more. Find the probability of 35 to 54 and no. Now we have two age groups, but the result is similar. We ask how many individuals are between the ages of 35 and 54, and also answered no to the question about special equipment. There are 762 individuals who answered no in the 35 to 44 age group, and 992 who answered no in the 45 to 54 age group, for a total of 762 plus 992, dividing by 6582, gives an approximate probability of 0.2665. These probabilities required no rule other than the relative frequency approach to calculating probability. Now we move on to a few examples of the probability of A or B when the events are not disjoint. We will answer the corresponding OR probabilities for the last two examples. We want to find the probability of 65 plus or yes, and the probability of 35 to 54 or no. We can do this using logic or the general addition rule, rule number 5. We will complete each using both methods. Let's start with the probability of 65 plus or yes. To determine the probability logically, we must count everyone who either answered yes or is 65 plus, without counting anyone twice. We need every frequency outlined in the 65 plus row and yes column. The easiest way would be to take the total for all those who answered yes, and then add that to the remaining individuals who were 65 plus, which would be 2422. This would give the probability of 65 plus or yes equals 978 plus 2422, all divided by 6582, or about 0.5166. Alternatively, we could take the total for those who were 65 plus of 3033 and add that to the frequencies in the yes column for those in the other age categories, 30 plus 117 plus 220. Or we could simply add all of the frequencies outlined in either orange or blue in the table, 30 plus 117 plus 220 plus 611 plus 2422. Any logical way we approach the question should result in the same answer. Notice that if we were simply to add 978 plus 3033, we would have double counted the 611 individuals who are yes and 65 plus. Subtracting away the 611 individuals would solve the issue, which is the approach taken by the general addition rule, which we will illustrate next. To use probability rule number 5, the general addition rule, to find the probability of A or B, we first need to have the three probabilities, the probability of A, the probability of B, and the probability of A and B. It is best to use logic and counting to find these values. In this problem, we need the probability of 65 plus, the probability of yes, and the probability of 65 plus and yes. We found the first and last probabilities before, but let's go through them once again. There are 3,033 individuals who are 65 plus out of 6,582 total. Dividing 3,033 by 6,582 gives the probability of 65 plus of 0.4608. There are 611 individuals who are both 65 plus and yes out of 6,582 total. Dividing 611 by 6,582 gives the probability of 65 plus and yes of about 0.0928. Now we need the probability of yes. There are 978 individuals who answered yes out of 6,582 total. Dividing 978 by 6,582 gives 0.1486. Now we can simply use rule number 5 to get the probability of 65 plus or yes equals the probability of 65 plus the probability of yes minus the probability of 65 plus and yes, which is going to be 0.4608 plus 0.1486 minus 0.0928 to get about 0.5166, which is the same value we found using logic alone. Now let's calculate the probability of 35 to 54, or no, using logic. We need to count all outline frequencies without counting anyone twice. The easiest way to do this is to take the total for the no column of 5604 and then add that to the frequencies in the yes column for individuals who are 35 to 44 and 45 to 54, which are 30 and 117 respectively. We could also use the row totals for ages 35 to 44 and 45 to 49, 792 and 1109, and then add the remaining uncounted frequencies in the no column, 1428 and 2422. Or finally, we could simply add all six numbers together, 30, 117, 762, 992, 1428, 2422. Whichever method we use, we should find that the probability of 35 to 54, or no, is 0.8737. To use probability rule number 5, the general addition rule, to find the probability of A or B, we need the probability of 35 to 54, the probability of no, and the probability of 35 to 54 and no. We found the last probability earlier, but let's go through all of these calculations here. There are 762 plus 992 equals 1,754 individuals who are both 35 to 54 and no out of 6,582 total. Dividing 1,754 by 6,582 gives the probability of 35 to 54 and no equals 0.2665. There are 5,604 individuals who answered no out of 6,582 total. Dividing 5,604 by 6,582 gives the probability of no equals 0.8514. We could also have found this using the probability of yes and the complement rule. Finally, there are 792 plus 1,109 equals 1,901 individuals who are 35 to 54 out of 6,582 individuals total. Dividing 1,901 by 6,582 gives the probability of 35 to 54 equals 0.2888. Now we can simply use the rule number 5 to get the probability of 35 to 54, or no, equals the probability of 35 to 54 plus the probability of no minus the probability of 35 to 54 and no, which gives us 0.2888 plus 0.8514 minus 0.2665, or 0.8737, which is the same result we found using logic alone. The most common mistake in applying this rule is in using a formula to find the probability of A and B. It is difficult to make this point clear until we cover the rules for the probability of A and B. But note now that we only use logic and counting to find the probability of A and B in the examples presented for finding the probability of A or B here, in other videos, and in the course materials. In the previous section, we introduced basic concepts of probability, including the relative frequency method of calculating probabilities from data and the law of large numbers, which shows us that in the long run, our estimates from representative data will approach the true value. In this section, we presented some of the basic rules of probability and illustrated how to calculate basic probabilities from data using both logic and the rules. We began with rules 1 and 2, which state some relatively simple rules of probability, that all probabilities are between 0 and 1, and that the sum of the probabilities of all possible outcomes must be equal to 1. The complement rule, rule number 3, states that the probability of the opposite of an event is 1 minus the probability of the event. The probability of not A is 1 minus the probability of A. We define disjoint events and discuss probability rule number 4, the addition rule for disjoint events. Be very careful when you are applying a rule that has specific conditions such as this. You must be completely convinced that the conditions are satisfied in order to use such a rule. You will notice that this rule is not listed on this slide, as I suggest using logic or starting from probability rule number 5, since it works for any pair of events. Then we illustrated how to find the probability of A and B by logic and counting. And finally, we discussed probability rule number 5, the general addition rule for finding the probability of A or B. We illustrated using both logic and the rule for finding the probability of A or B from data. You should notice that the types of examples we present in the course materials, videos, and quizzes are all very similar. You can expect to see questions like these again.